Evaluating limits for multivariable functions is very similar to evaluating limits of single variable functions. We get to carry on a lot of the rules that we learned in Calc 1. For example, if we happen to look at two functions like f and g, and we know the limits of those functions as they approach the point x0, y0, then we can make some quick shortcuts to help compute limits. If I were adding f and g together, I don't actually have to add the functions together and then calculate the limit. If I already know the limit of f and I know the limit of g, I can just add those two limits together. In short, the sum of a limit is the limit of the sum, so we can interchange these two. It also works for subtraction, so if we're finding the difference between two functions, we could simply just find the difference between their limits. If we're multiplying a single function by a constant multiple, then we can just multiply the limit of that function by the multiple. If I have the product of two functions, I can just multiply the products of their limits. Same with quotients. If I'm doing the quotient of two functions, I can just do the quotient of their limits. A power rule also applies the same way. We can sneak the limit inside of the exponent here, apply the limit to the function, and then simply just raise the limit to the exponent. And same with roots. So everything that we did for single variable functions, for sums, differences, constant multiples, product rules, quotient rules, they all still work for limits on functions of several variables, which will make finding a limit, computing a limit, or evaluating a limit pretty simple. Most of the time, it's going to be direct substitution. So I look at the function, I see, for example, this top one, my point xy is approaching the point 0, 1. And the function that I'm looking at, I'm not going to read that out loud, that's pretty extensive. All I need to do is replace x with 0 and replace y with 1 based on the point that I'm approaching. So in my function notation, that would look like 0 minus 0 times 1 plus 3 in the numerator, divided by 0 squared times 1 plus 5 times 0 times 1 minus 1 cubed. And then we simplify, 3 on top and minus 1 on bottom. So we get negative 3. Now, if you think back to when you first learned how to compute limits, the ones that were really difficult were the ones that took indeterminate form. And I'm not really going to bother you with too much of that in this class. You should still remember how to do the algebra to get out of an indeterminate form. And I need to remind you that 0 over 0 is not equal to 0. It is indeterminate. So if you evaluate a limit, and instead of getting 3 divided by negative 1, for example, if instead you got something that looked like 0 over 0, you would need to stop and say, I don't know what this equals. Let's go back and try to do some algebra to clean it up. Most of the time you can simplify just by dividing off common factors in your numerator and denominator. Maybe you need to do a substitution. Maybe you need to multiply by a conjugate. But just remember that 0 divided by 0 is not an answer. Let's go through and evaluate just a couple more to show you this really is as easy as you would like it to be. In our second limit, we're looking at the square root of x squared plus y squared. Our limit is approaching the point 3, negative 4. So I'm going to do direct substitution. Plug in 3 for x and negative 4 for y. And simplify. I'm not going to do these other examples because I feel like at this point this is algebra that you can handle. So make sure to give this some practice, evaluating limits, and just remember if you get to 0 over 0, you don't have an answer there. That just means go back and do some algebra. In Calc 1, you might have learned that sometimes two-sided limits don't exist. And we learned that by looking at single-sided limits. For example, if I were to look at the limit where I'm allowed to approach 3, then from the left, as I'm traveling on my function coming from the left, I'm traveling on this blue line. Let me use a different color. Traveling on my function until I reach the function output that's directly above x equals 3. So my left-sided limit looks like, as x is approaching 3 from the left, looks like I'm coming to 2. And for the right-sided limit, I would just travel on my function coming from the opposite side until I'm directly above the x value 3. And I get the same thing. It looks like my function's approaching 2. It's too dark. Because my left and my right-sided limits agree with each other, I know the two-sided limit must also be equal to 2. However, sometimes our functions are more complicated and it doesn't end up looking like that. So let's try another scenario. This time, let's look at when we approach x equals 1. Now coming from the right, we're traveling on our function. It looks like we're approaching the point 1. So coming from the right, our limit is approaching the function value 1. However, coming from the left, traveling on our function, it looks like we're approaching the output 0. Since the left and the right limits are not equal to each other, the two-sided limit does not exist. The same idea is going to be used to show when limits do not exist for multivariable functions. But here's the trick, that we can approach our point from infinitely many directions. In single variable calculus, we're working with two-dimensional functions. You either come from the left or you come from the right. But in multivariable calculus, we're working with functions that have at least two independent variables. And approaching a point in a plane, you can travel in any path you want. You can swirl around it, you can zigzag there, you can go straight to it, which means there's infinitely many directions that you can come from. We're not just coming from the left or coming from the right. But the thing that still works is that if you can find two paths that approach different values, then the limit cannot exist, just like from Calc 1. Just like when we were approaching x equals 1 in this limit, coming from the left, we were going to 0. Coming from the right, we were going to 1. Those two things don't agree, so I know that the limit as x approaches 1 for our function does not exist. In multivariable calculus, you might find 3, 4, 5, 20, 100 paths that do lead you to the same point. But if you can find exactly 2, that's all it takes, just 2 paths that lead you to different output values, then the limit does not exist. Let me show you an example of what I'm talking about. On the screen, you see the function f of x that's graphed in 3D, some surface. And it kind of looks like maybe a piece of paper that somebody has pinched to pick it up off the table. And I want to show you that when we get towards the origin in the domain, so at x equals 0, y equals 0, some funny stuff happens. First, let's travel towards the origin, but we're going to travel along the path that comes from the relationship x equals negative y. So if we only pick domain points that follow the line x equals negative y, we can travel along the function output along that path, and that's the green curve you see on the surface. And that path will lead us to the origin. And we know that because x equals 0, y equals 0 satisfies that expression x equals negative y, because 0 does equal negative 0. So traveling along that green path, or traveling along this yellow path. So the yellow path is also leading us to the point 0, 0 in the domain, but it's traveling along x equals positive y. We can see that we're traveling along two separate paths that take us to the same place in the domain, but as far as the function's concerned, we're going to completely different places, and we can see that there's a gap right here. The green path is taking us to some point down here. The yellow path is taking us to some point up here. That is not an infinitely small distance between the 2 points. So because there's space between these 2 points, we know the limit does not exist. If the limit did exist, then all paths, every single path that you could possibly imagine, and those that you can't even imagine, all of them that go through the origin would lead you to the exact same function output. But that's not what happened here. We've got two different function outputs, even though we're going to the same spot in the domain. Showing that a limit fails to exist comes down to finding two paths that give you different limits. So we're going to start by finding the simplest paths. If we're looking at a domain point xy approaching the point 0, 0, I need to find two paths that go through this point. The easiest paths I can think of are x equals 0 and y equals 0. Both of those lines will pass through the point 0, 0 in the domain. If I travel along each one of those paths, I can see what the function looks like. So, for example, along the path x equals 0, our function 2xy becomes 2 times 0y. And when we're dividing by 3x squared plus y squared, that looks like 3 times 0 squared plus y squared. The numerator reduces to 0. The denominator reduces to y squared. Now, if we're looking at the limit where xy is approaching 0, 0, and the expression we're looking at is 0 over y squared, really we're saying what happens when y gets close to 0. Now this is an easy trap to fall into. If we simply jumped to y equals 0, we would get indeterminate form. Which means we need to go back and simplify. Check and see, can we simplify? Well, we have 0 in the numerator, and in that case, as long as y is not 0, 0 divided by a non-zero number is 0. And because our limit is saying let y approach 0, we can say that really we're looking at every number except y equals 0. So we can simplify 0 over y squared to just be 0, which means we're really looking at the limit where our domain point is approaching the origin of a constant 0, which that of course would be equal to 0. So along x equals 0, our limit is saying that the function approaches 0. But what about along y equals 0? In that case, our function would look like 2x times 0 divided by 3x squared plus 0 squared. That simplifies to be 0 over 3x squared. And again, we're looking at the limit as xy approaches 0, 0. of 0 over 3x squared. We get the same indeterminate situation, but since x is approaching 0, we can assume that until we get to that point, that x is non-zero. We can simplify. We're looking at xy approaching the origin of a constant 0, which of course is equal to 0. Now here's where we need to be careful. Remember, our goal is to find two paths that give different limits. We found two paths that give the same limits. Basically, that says our job is not done. Finding two paths that give the same limits is not the same thing as finding two paths that give different limits. So, although we did a great job finding the function limit along each of these paths, we need to find a third path. Maybe a fourth path, maybe a fifth path. We're going to keep going until we find a path that contradicts what these other two have said. Looking for an additional path, we need to make sure that it still passes through the origin. I like using lines because they're easy to work with. So maybe we use something like x equals y. I know that that line does pass through the origin, so that's fine to use that one. And since we did the work for these two, let's make some room here. I'm going to keep the first one we did, just ditch the second one because it did not add any value to our solution. And I'm going to travel along x equals y. So in that case, I'm going to replace all of the y's with x. So I'll have 2x squared in my numerator, and then I'll have 3x squared plus x squared in the denominator. That simplifies to 2x squared over 4x squared. My x squareds will divide off. I have 2 over 4, which simplifies to 1/2. Now let's go back to our limit. If we're letting a domain point approach the origin for this value along the path xy, then our limit is just approaching the constant 1/2, which is equal to 1/2. So along this path, our limit disagrees with the other limit. We found two paths. Path 1 along x equals 0. Path 2 along x equals y. The limits along those paths do not agree, therefore the limit fails to exist.